right, you're welcome back. Now we are trying to uh, look at normality assumption. Normality assumption. That's what we are looking at. Last time, if you follow carefully, we used Shapiro test to check our normality. If data is normally distributed, we discovered that there's only one column that passed the test, which is a separate width. I don't know if you still remember. So if you don't watch that, you can watch under Shapiro. Please go back and watch that so that you can follow up from there. Okay. So because you see, I need to make a reference to that while we continue on this section. Okay. So the other three numeric variables, the failed Shapiro test, only one passed the test, which is a separate width. All right. So Shapiro is not the only one. We can also use graphical method to check our assumptions for normality, and one of them is called histogram. Histogram is a very good graphical plot that we use to also check our normality in past. So the same way we do in another application or in another programming language. So we can use, don't forget this data set was copied from from a Excel, okay, to this place. So don't forget. So copying the data from here, it shouldn't be a challenge anymore. So if it has to be a challenge, say you have to watch a previous video to know how to move your data in. So we are going to just go ahead and perform the test here. I'm trying to minimize the number of hours or minutes of videos, so that it won't be too long. Okay, that's why I'm trying to break it down into small clips. Okay. All right. So now we want to test each of them again. Let's look at this one first. We want to look at the histogram, see if it meets the test. So there is a way the bell, okay, should look like. Right? I'm talking about the kernel density now. So you call it the bell. The shape is called the bell. How it should look like when it's never distributed. So it must be fitted. Okay, let's look at plot first under the histogram. Okay, look at the histogram here. Okay. Right, so now looking at this now, the way if you click on fit normal, this is how the bed should look like. This is how the bed should look like. But to don't fit normal, this is not the correct result. Okay, this is not a real result. Okay, the result is kernel, right? But we just want to compare. The purpose of using fitting kernel is to compare with kernel density. I mean, the purpose of fitting normal rather is to compare with kernel density. Kernel density is your main result. You want to feel if your data is normally distributed, you use what kernel density. But we first feed normal to see the normal distribution, which is accurate. This is accurate distribution, but this is not your real data. Okay, this one just showing you the shape, how it should look like. So when you now say kernel now, you can see if you remove this guy now, you can see your shape now, how it look like. This is your own data shape now. Okay, this is your data shape. So this one is not normally distributed. You can see how it look like. It does not look like this one. All right, you can see. So you show that it's not normally distributed. Okay, because the shape of the bell is not in the proper order. So you can discard this. So let's try another one again and see what I'm talking about. Okay, let's try this. All right. Don't forget, this one was last time was significant. I mean, was past the test. Okay, it passed Shapiro test. Okay, but not significant. So we can see again in our graphical and see if he truly passed the test or truly. So if you close, it's close to normal division, not exactly, not that perfect, but I think it's very close. All right. So now let's fit it. If you fit it now, you can see how it look like. All right. So if you fit now, can you see it's very close to kernel? Can you see? Even though it has a long tail, okay, like the peak is high, okay, the peakness, peakedness is very high. So, but it's very close to normal distribution. Can you start to see the shape of the bear? All right. So it shows that it's normally distributed. So it's very close to normal distribution, very close. So we can assume that this particular one passed normal distribution. We can assume that. Okay, if you can, maybe you can, let's do one more and confirm before we leave this one. So let's do one more. You can see the difference between each of them. All right. Okay. So let's fit normal with normal. This normal distribution. All right. So when we fit kernel, you can see. Look at this. I look like. Can you see different from that one? Okay. Let's do last one here. I just want you to see the difference so that you can even you understand the shape, how the shape look like. Then you'll be able to conclude. So look at this again. Okay, this normal distribution. So let's look at our kernel. Can you see how it look like? It's like sinusoidal. So it is not normally distributed. It's very obvious. So only sepa width that shows a kind of normal distribution. Right? Only this. All right. Only this. Okay. Only this. Can you see? Only this one. You can see. So Shapiro was not wrong. It wasn't wrong. Shapiro wasn't wrong. Shapiro showed that it is close to normal division. That's what it should, because of we have 0.1. So it shows that it is close to normal distribution. That is what Shapiro tells us. So it also shows here that it is true. Shapiro was correct. So you can assume that this particular column or variable is normal distributed. You can agree upon that now by using our both Shapiro as a statistical test and also graphical representation. So you can conclude that this particular column is normally distributed. All right, so that is how we'll stop today. In the next class, we also go further to do other tests again. Thank you so much for listening. I will see you also in the next class.